So now I'm recording. So let me start what we started on yesterday. So the idea here is to calculate the density of state. Okay. Density of state. So what is the meaning of density of state? Is I want to calculate the number of energy levels in per electron volt. For example, if I take DE, a small band, how many energy levels do I have here? Just because those energy levels are the ones that represent or that define the thermal properties of the materials, and you will see how later. Okay. So what we did yesterday is we started by the we did the approximation for the metals, and for the metals the energy levels are equal to n squared h squared over 8m per squared. L is the length of the potential, and m the mass of the electron, h is the Planck's constant, as n in 3 dimensions, n is equal n squared x plus ny squared, the quantization along x, along y, and along z. Okay. So what we did, if just to review very quickly what we did yesterday, we took, let's say this is nx, this is ny, and this is nz. So nx, ny, nz are all of them are integers that goes from 0 to infinity. So 0, 1 to positive integers. So this means I will have, for let's say, just give an example, nx, ny, nz, all those states I have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, yeah, so 0, 1, 1, and then 0, 1, 2, and then 0, 2, 1, and so on. So all the combinations of integer values. So I will have, for example, a point here, a point here, point here. This is okay. So any combination of this, so here, any combination, I will have a state. So this means if I take any cube, any small cube, let's say I will take this cube. So each cube has a volume of one state. So each cube have a volume of one state. This means the number of states, the total number of states is just the total volume. The total, if I take a sphere, for example, here, a sphere, and this sphere has radius n, so then the number of states will be the volume of the sphere. Why? Because one unit, one cubic unit, 1 point is equal to the volume of one or the energy state, one energy state. So this small cube is equal to one energy state, and this means that the total volume is this number of states. So the number of states is the volume of the sphere. Okay, is the number of the sphere. In fact, this is exactly, if you take a large volume, let's say, to make it clear for you, if I take a large volume, a cubic volume, okay, and this volume is made of a small cubes, okay, let's say this is a small cube, this is another cube, Okay, this is another cube, and so on. So if you want to take the total number of cubes, so if each cube is one state, so what is the number of states? It's just the total volume. Okay, because the total volume give you the number of small cubes if those cubes have a unit 1. So the volume of the sphere, and the volume of the sphere, we know it is equal to 4/3 pi n cubed, because n is the radius. N is the radius of the sphere. So this is the number of states. The number of states. Now, what is n squared? What is n? N is also equal. So if you remember, we get n, the energy is equal to 8ml squared, which means n squared is equal to 8ml squared, the energy divided by h squared, which means n is equal 8ml squared E of h squared 1/2. So the number of states that have energy, the energy smaller or equal E, which is inside the sphere, is 4 pi, 4/3 pi, n cubed. N cubed is, I will take this and put it cubed, raise it to the power of 3. So this will give me 8m L squared E over h squared and to the power of 3/2. This is the number of states having an energy less than E. So all this sphere, all this, all those states that are here, all those states, those ones, they have an energy that are less or equal to E. Any question? Any question about this?
No, Professor.
Okay. So now yeah, so what I can do, I can simplify this. This is 4/3 pi, okay, and this is yeah, so 8m L squared over h squared to the power of 3/2, and then the energy 3/2, which I can also write as 4/3 pi, a constant 3/2 E. With the constant, I would just put this, take this as a constant, h squared. Okay, this is a constant. Okay, so this is the energy or the number of states that have energy between 0 and E. What do we want? Let me go back to our original plan. Original plan I want to know how many states do I have in a very small element. So then what I can do the following. I know that, again, I will do this drawing. If I take this sphere, this is N, this has an energy, this is the number of states that have energy less than E. Okay. And I want to calculate if I take dE, so the blue curve is the number of states that have energy smaller than E plus dE. Okay. So this means the red part is the one that I want to calculate. So this is dE. This will give me the number of states in dE, in this very small element of dE. Okay. So how do I do this? Let's calculate the first thing. What is the number of states that have energy below E plus dE? How can I calculate this? How can I calculate the number of elements of state, sorry, that have energy state, that have an energy smaller than E plus dE? How do I do it?
You just add the derivative of the first equation you showed us like a second ago to the
So,
same equation, right?
so what I can do is the following. I know that for any energy, the number of states below that energy is this. I can just use the same formula. So it's 4/3 pi k and then E plus dE to the power of 3/2. Do you agree? Okay. Do you agree?
Yes.
Because I define what I did above. I define the number of states in any energy. Okay. So now I can apply. So this is the number. This is the number of states below E. This is the number of states below E plus dE. So if I want to calculate the number of states, in dE, in this layer, I don't know why everything became in this layer, dE. All what I have to do is this number, I will call it this number NE, and this number I will call it NE plus dE. All I have to do is to do the difference between the number of states that have an energy less than E plus dE minus the number of states that have energy less than E. Do you agree? Is this clear? Hello?
Yes, Professor, it's clear.
Okay. So, well, this means that this is equal to the constant of E plus dE power 3/2 minus E. Okay. So this is the number of state. I want to simplify this. Now, we have seen that the E dE is very, very small than the energy. If you remember, we got that for 3 electron volt last session, not the session of yesterday, but the day before. 3 electron volt. dE is of the order of 10 to the minus 7 electron volt. Okay. We have calculated this. So dE is very, very small. So what we can do to simplify this, we can use Taylor expansion. So who can remind me of the Taylor expansion? You have seen this in calculus, right? I think in calculus 2. So Taylor expansion tells us that I can approximate A plus H. a function, let's get a continuous function, and this continuous function, I want to approximate f of a plus h. This is equal to f of a plus this difference h, and then the derivative at point A. This is the Taylor function. Do you remember this? Taylor expansion. Okay. Do you remember this or not? So now let's apply it. Let's apply it to our function. Our function is e plus dE to the power of 3/2 will be equal, what is the function f here? Our function is equal to e to the power of 3/2, okay, f of e, okay? And f of e plus dE is equal to e plus dE to the power of 3/2. So e plus dE to the power of 3/2 is equal to the function itself at a, which is at e, plus dE times the derivative of this function. What is the derivative of this function? 3/2, and then e to the power of 1/2. Just because the derivative of 3/2 with respect to e is equal to 3/2 e to the power of 1/2. Are you following? Is this clear for everyone?
Yes, Professor.
So now let's replace. Let's replace in this. So in this I have 4/3 by the constant 3/2, okay? E plus dE, I can replace it by its value. So it's E 3/2 plus 3/2 dE e to the power of 1/2, and then minus this one, minus e to the power of 3/2. And you can see, we will get rid of this, The number or becomes 4/3 by k to the power of 3/2 times 3/2 e to the power of 1/2, and then dE. So I can get rid of this, and this becomes 2. So it becomes 2 pi k 3/2 e dE. This is the result that I'm looking for. Not yet, but this is the number of states in dE. Is this clear? So let me again start. Just repeat a little bit, just to so that you don't lose track of it. So what I wanted to know is how many energy states are there in dE? Because we have already proven that the energy levels are so close that we can take the energy state as a continuous function. Okay? So what I want to do then is to calculate how many energy states are there in a small element dE. Why? Because if I can define this energy, the density of state, I can use it to calculate many things about the material, about the metal in this case. So we started from the energy level of the metals that we know, with the approximation from the solution of Schrödinger's equation. And we defined a sphere in this sphere, each the sphere gives us the number of states that have energy less than, or the integer number less than n, which means an energy less than E, because for each set of integers, there is a number of energy corresponding to it. So the number of the state is the volume of the sphere. We calculated the volume of the sphere, which is this one, but we know also that n, we can get it from the energy. So there is the Schrodinger's equation gave us this relationship. Then the number of states that energy that have an energy, the number of states where the energy is less than E is this. Okay. By the way, this is just a constant. It has nothing to do with the wave number, please. It's a constant. It has nothing to do with the wave number. Okay. And then we are interested to see how many states are there in a small element dE. So then what we can do is to calculate the number of energy states in E plus dE. We apply the same formula and we got this one. Now, if I want to calculate the number of energies in that element, all that I have to do is to do the subtraction between these numbers, which gives me the number of states that have energy below E plus dE, and this number that gives me the number of energy levels or state that have an energy less than E. And this is what I did. So this one minus this one, which gives me this one. I want to simplify this, and I know that the energy I'm looking at, the layer that I'm looking at, is very, very small compared to E. This we have already calculated. For example, for 3 electron volt, we have seen that it is 10 to the minus 7. So I can use the Taylor expansion. The Taylor expansion tells me that if I take a function at any point x, and I want to calculate a plus h, then it is equal to the function at a plus that h times the derivative of that function at a. Okay. Actually, it's if you look at the derivative, what is the derivative? Derivative of point a, the formula of the derivative is equal to it's equal to fa plus h minus fa divided by h. This is exactly what you get here. This is the formula of the derivative. Okay, so if I do this, I apply it to the function e to the power of 3/2, then I get this. I plug this in this formula, in this equation, and then I obtain a very simple equation. The number of states that have an energy less than E, any E, is equal to a constant times the energy to the power of 1/2. Okay. Is this clear? Now, there are two remarks here. Two remarks. So if you have any question, it's better to stop me now. Okay. So I assume there is no question. Now, let me also give you another question here. So what we did is nx, ny, nz. Okay. And as I mentioned, nx, ny, nz are taking positive values 0, 1, 2, 3, and so on. All of them. However, when we calculated the number of states, we took a sphere that is centered around 0. And this sphere, because it's centered around 0, the total volume of the sphere is taken into account also the negative values of ny, negative values of nx, okay, and the negative value of nz. So the sphere is centered around 0, and we are taking, when we calculated the number of sphere, the volume of the sphere, which is the number of all values, we also took into account the negative values, which doesn't make sense. So we have to take into account, so our treatment remains valid, except that we have to remove all negative values of nx, ny, and z. We should keep only the positive values. What is the proportion of the volume of the sphere that I have to subtract? Are you following?
The bottom left.
Okay, so let me just make it simple. Make it simple. Let's start by the following. Let's start by 2 dimensions or 1 dimension. Let's start by 1 dimension. Okay. In 1 dimension, I start from 0. If I take all these are number of states that I took, at the end, what will be the number of states that are really positive?
The ones that are greater than 0.
Yeah, so I have to, so only these ones, right? So I have to subtract this one.
Yeah.
So this means that I have to divide this density of state that I found by
2.
exactly by 2. So in 1 dimension, I have to subtract. So in 2 dimensions, let's say this is nx. Okay, let me make it very clear so that you can understand. So in 2 dimensions, I have nx and ny, right? So for nx and ny, in order to have a symmetry, I'm taking the whole disk, the area. So then it will be pi n squared, the area. And this area gives me everything. Now, once I do the treatment and I calculate the density of state of all this area, by how much I should divide the final density expression of the density to account only for the positive values of nx and y, ny. Hello? If I take all this area, okay, all this area, and I calculate the number of states there, and I get a number of states, density here. But I know that I should only take into account the positive and values of nx and y. The positive values of nx and y represent this part. So my density of state should be divided by which number?
Divided by 4, right?
Yeah, by 4. So this is 2D. Now, if I go to 3D, in your opinion, I should divide by how much?
8.
I should divide by 8. So the first, to account for positive values of nx, ny, and z, positive values only, or for only positive values, I have to divide by 1/8. Okay, I have to divide by 1/8. This is the first thing. So this quantity should be divided by 1/8. This is the remark number 1. Remark number 2, electrons are particles that are called fermions. And because of the exclusion principle of Pauli, you cannot have more than one electron having the same, or two electrons cannot have the same. So you can have maximum, you can have two electrons, one up and one down in one state. Okay, you cannot have more than one. So you can have in one state, you can have an electron up and electron down. So this means in each state you can have up to two electrons. So you have to multiply by 2. Please don't forget this. So this is the exclusion principle of Pauli. Exclusion principle of Pauli. You remember we have a state here, an energy, and then I can only have, well, I can have 2 electrons, up to 2 electrons here. So you have to multiply by 2. So this quantity that I calculated here, 2 pi, I will replace k. K is 8ml squared over h squared to the power of 3/2. And then the energy 1/2. Okay, I have to multiply it by 2 and divide it by 8. Okay, so this is, so I can give you the final density of state. So the final density that we will be using, we call it ZE, and it is equal to a constant C to the power of 1/2. And this C, so this is a C times, okay, and the power of 1/2, and the C is 4 pi L cubed over H cubed. This is the density, sorry, wait, I'm not done yet. And then times 2 times the mass of the electron, 3/2. Okay. This is the density of state. So what does this mean? It means the following. If I take any element here of energy, well, I can calculate how many energy states I have in this element. So this will give me for any DE, I have Z. Any question? There is also another thing that I wanted to mention here. So this is the density of state. This is density of state for metals. You can see that here this is L cubed, which is the volume. L cubed is the volume of the well, of the well inside which the electron or the particle is, the volume we are looking at. In some textbooks, and also in the textbook you have, they are also talking about the density of state, the density of state per unit energy, and they call it it's the same, except that is equal to that density that we calculated divided by L cubed. Okay, so they just take it per volume. So it will be the same, except that L cubed will not be here. So it will be 4 pi H cubed 2m to the power 3/2, and then e to the power of 1. So you will see that in some textbooks, they take this one, so there is no L cube here. Any question? Now, let me just mention something about if I want, so now I have the density of state, the density of state. Let's assume I have a metal. This is the energy of a metal. And I want to calculate, I want to know what is how many energy levels between 2 electron volt and 5 electron volt. Let's say in the metal, for some applications, I want to know how many energy levels, how many do I have between these 2 electron volt and 5 electron volt. What do I have to do?
Don't we integrate it?
Exactly. So what we do, yeah, so the total, the number of energy states, we just integrate from 2 electron volt. We will do several exercises about this. And then ZE dE. Now, ZE is a constant. So it will be C from 2 electron volt, 5 electron volt of e to the power of 1/2. Now we know that this is an easy integral. So what is the integral of e to the power of 1/2? I need someone else, huh? I need you to write in the chat. This is a very simple thing, but I just want to make sure that the others are not really just sleeping. Okay. Okay. Yes. I have an answer from Reem. Okay. Who is else? Anyone else? I don't want the derivative. I want the integral. So what is the integral? I know it's an easy, but I just want to check that you are following also. Okay, I will not mention the name because we are recording, but yes. Okay. Okay, okay, yeah, so 2/3 e to the power of 3/2, okay? So 2/3, so it's 2/3 c e to the power of 3/2 from 2 electron volt to 3 electron volt. I will not do the calculation to, what was 2 electron volt to 5. I will not do the calculation for the moment because we will talk about it, how to calculate this because remember, you have to do some conversion, but we will do some exercises here. Because remember, this is the Planck's constant is given in joule second. And if you want to and the energy is given in electron volt here. So you need to convert one of them. And so you need to convert the Planck's constant, so the electron volt second. As we will do some problems here. I just wanted to tell you this is one of the usefulness of the knowing the density of state. Okay. So any questions? So I will stop here now and go to something else.
Professor,
Yes.
do we replace the E with 5 electron volts, or do we
Yes.
solve it at
Yes.
the end?
So
Or
yeah. So this is what I wanted to mention. What I said, I just give you here an example, but later we will do the calculation. What I just said is yes, of course you will replace, but the total value you have to take into account the fact that your constant has a Planck's constant, okay, and Planck's constant is in joule second, and the energy is an electron volt. So this is an energy unit, and this is an energy unit. So you have to convert everything to electron volt. Okay. But
okay.
yes, we will replace it. Okay. So let's go to another page. So the density of state. The density of state now, it's very simple. Density of state is density of state is we just calculated that is a constant. Very simple. Okay. Now if I look at the energy levels, for example, let us see what we have discussed yesterday or the day before yesterday about a metal. We have seen that the metal, let's say for lithium, for example, it has an area which is fully packed, occupied, full occupation, sorry. Okay. And then you have an area which is empty. It is a load, but it's empty. And then you have, of course, outside the metal. And we have seen that this is the work function. Okay. So now, how do we know that those areas, so let's say this is a state, this is a state, this is a state, this is a state. So all those states, they are occupied by electrons, but those states are empty. So if we want to calculate the total number of electrons in the metal, we need to take into account the occupation. So not only the density of state that is important, but also the probability, the occupation probability, the occupation. So we need to calculate or to know the occupation probability. Probability for those states, for the state. What is the population probability? For example, this one is an empty, so its population probability is 0 for the moment, unless you provide electric field or external potential difference. Same thing. For this one, the probability is 1 because it is fully packed. So how do we know this, the occupation probability? Now, the occupation probability, let me talk about the particles. So there are, according to the spin, as far as the spin, if you remember the spin of the particles, the particles are classified into things, into fermions and into bosons. The particles called fermions are those particles that have a half integer spin. For example, 1/2, minus 1/2, 3/2, and so on. Those are particles that have a half integer spin, like electron, like positron, okay? And particles that have full integer spin. Full integer spins 0, 1, 2, and so on. Those are particles that are completely different. Their behavior is completely different. The way they occupy the energy state is completely different. In fact, why they are called fermions and why they are called bosons. Fermions, they are called fermions because they follow or they obey Fermi-Dirac statistics. What is Fermi? Is Enrico Fermi, the famous scientist who contributed to the Manhattan Project. Dirac is Paul Dirac, the famous British scientist, who was the first one to couple the quantum mechanics and relativity of Einstein. Okay, so Fermi-Dirac statistics is used for fermions. That's why they are called fermions. And what are fermions? Fermions are particles that have half integer spin. 1/2, minus 1/2, minus 2, 3/2, 3/2, etc. Bosons are particles that obey what we call the Bose-Einstein statistics. These bosons. And this is, so Bose is an Indian scientist, very famous scientist, and Einstein, all we know Einstein. So this is the difference between the particles as far as the spin is considered. The particles are particles called fermions, particles called bosons. Because we are dealing with electrons, we will use Fermi-Dirac statistics. Fermi-Dirac statistics is the following. So the Fermi-Dirac distribution, Fermi-Dirac distribution. Here, if you don't understand, just stop me. If you are losing something, I mean, some understanding or some concept, just stop me, because this is very important, and we will use this in semiconductors. So the Fermi-Dirac distribution and statistics, they explain to us what we see in metals and what we see in semiconductors. Okay. So what is the Fermi-Dirac distribution? The Fermi-Dirac distribution is the probability of occupation of an energy state. So if I take, as I mentioned, those energies here and there, I will take those ones, for example. Fermi-Dirac distribution will give me, well, the probability for this to have an electron, or the occupation, is that number. And the probability for this to have an electron is that number. Okay. What is the Fermi-Dirac distribution? The Fermi-Dirac statistics of distribution is a very important quantity in physics and electrical engineering, is 1 divided by exponential of the energy minus energy, a quantity called EF. I will talk about it, KT, and then plus 1. So this is the Fermi-Dirac distribution. So what is E? E is the energy of the state I'm talking about. Energy of the state. I'm talking about. EF is a quantity that is very important. We will talk about it. It's very important in metals. It's very extremely important in semiconductors. You will see that this quantity will play a major role in p-type, n-type, p-n junction, of the semiconductors. This is called Fermi energy or Fermi level, or Fermi energy. Of course, the energy here is always given in electron volt. K is the Boltzmann constant. And T is the temperature. So the Boltzmann constant, so the Boltzmann's constant is given in electron volt per Kelvin or joule per Kelvin. Now you have to take make sure that you are using the right unit, but we will do some examples. Temperature in Kelvin. So this is the Fermi-Dirac distribution. Okay. Now, what does this Fermi-Dirac distribution? It gives us the probability of occupation of a given state. Let's start by. Are you following? Is there any question? Is there any question here?
No.
So again, we define the density of state. What is the density of state? If I take a layer delta E, I can use this density to calculate how many energy states are there, right? This will be given by the density of state. But I also want, what is the probability for this state to be occupied? What is the probability for this state to be occupied? This will be given by the probability occupation. Okay, so let's talk about some extreme cases. One, exponential E minus EF AT plus 1. Now let's take T equals 0, a metal at low temperature, very, very low temperature. We know that when T is equal to 0, well, 1 over KT goes to infinity, right? Now we have two cases. If the energy, if E minus EF is bigger than 0, this means that E minus EF over KT goes to plus infinity. This means that 1 over exponential of this plus infinity goes to 0. Are you following? So if I do the following, this is the energy. This is the Fermi level, Fermi energy. And this is the probability of occupation. Please follow here. I have obviously two cases. Either I have energies smaller than EF or energies bigger than EF, of course, or E equal EF. If at T equals 0, this quantity goes to infinity. And I have two cases. Either the energy is bigger than EF, my energy is here. If the energy is bigger than EF, this means that this quantity is positive, so it goes to plus infinity. If this quantity goes to plus infinity, my function, 1 over exponential of plus infinity plus 1 goes to 0. So this means at T equals 0, all those states here will not have any occupation. There will be no electrons. Are you following? Is this clear?
Yes, Professor.
Then, the second case, this is case number 1. Case number 2, well, E minus EF is smaller than 0. Let me use another color so that you know this. Second case is E minus EF smaller than 0, which means I'm talking about this region. This means that E minus EF over KT goes to minus infinity, because this one goes to infinity and this one is negative, so it goes minus infinity. Well, what does this mean? Exponential E minus EF over KT goes to 0, because exponential of minus infinity is 0. Well, this means that FE, which is 1 over exponential this plus 1, it is equal to what? If E minus EF is less than 0, which means energy that are levels that are less than the energy, the Fermi energy, this will go to infinity, minus infinity. Exponential of minus infinity is 0. So f of E, which is 1 over exponential of this quantity, plus 1. This one will be equal to what?
It will be 1.
It will be 1. So all the energy levels here, they will be fully occupied. So this is at t equals 0. In other words, this is exactly what we did, if you remember the first 2 days ago. If I take the metal at t equals 0, the metal, I told you there is always an energy levels below which at t equals 0, all energy states are occupied. This is the Fermi energy. Fermi energy here is full. And above Fermi energy, this is empty. And of course, this is outside of the metal. Is this clear to everyone? Okay. Any question?
No, Professor.
So now, again, just to summarize, we talked about the probability, the density of state, the density of state that gives us the number of energy in any layer of energy, any band of energy. And for each of that energy state, we need to calculate the probability of occupation. Now, obviously, the metal, you will see, you can easily prove that when the temperature increases, what happens is the probability here starts increasing, which means when you increase the temperature, some of the electrons start going this. And in fact, when you increase the temperature, you will see that the behavior of this changed. And the energy levels that are empty, they start to get a non-zero occupation values. Okay? So we will talk about this tomorrow, and then we will start then calculating the total energy of the system, the total number of electrons, and we will compare it to experimental values. Okay? And we will also calculate the specific heat values and so on. Any question? If not, I will stop here and I will see you tomorrow. I will not be able to upload the video now, but maybe in 3 or 4 hours from now. Okay? Thank you.
Thank you.
I will stop recording.